Hello, everyone. Welcome. Hi, I'm Oliver.
Hi, I'm Lily.
Science and Easy English.
How fast can a human actually run?
And today we are setting out on a truly fascinating mission for this deep dive. I mean, we have an incredible stack of sources in front of us.
We really do.
We are pulling from advanced biomechanical physics, cutting-edge genetic studies, and even, well, real-world anomalies that completely defy everything we thought we knew about human sprinting.
Right, and our goal is to unpack all of this research to answer one ultimate question. What is the absolute biological limit of human speed?
Which is such a massive question.
It is, and the reason this matters to you, the listener, is that the mechanics of how our bodies move through space are absolutely mind-blowing.
Oh, completely.
Whether you are actively trying to shave a few seconds off your 5K time, or you're just sprinting down the sidewalk to catch a bus before the doors close.
We've all been there.
Exactly. Or maybe you are simply insanely curious about the limits of human potential. Understanding what actually makes us fast changes the way you look at the human body.
It really does.
It is so much more than just putting one foot in front of the other.
Okay, let's unpack this, because I think the biggest misconception out there, and I know I certainly believed this before looking at the research, is that to run faster, you just need to move your legs faster.
Which makes intuitive sense, right?
Right. You see an Olympic sprinter blurring down the track and you think, wow, their legs are just spinning like a cartoon character.
Like they just have a faster internal motor.
Exactly. But the research from Dr. Peter Wayan's Locomotor Performance Laboratory proves that is a complete myth.
The data they collected completely upends how we think about running.
It's wild.
They study everyone from elite world-class sprinters to, slow joggers doing a weekend lap around the park.
Basically everyone on the spectrum of fate.
And they found that the universal timing of human leg movements is essentially identical across the board.
Wait, identical?
Basically, yes. The aerial time, which is the amount of time you spend floating in the air between steps, is about 0.12 seconds for almost everyone.
Just 0.12 seconds.
Right. And the time it takes to swing your leg forward for the next step is just over 1/3 of a second.
So fast or slow?
That internal clock of leg turnover barely changes at all.
Wait, hold on. You were saying that my clumsy, heavy-footed jog around the neighborhood has the exact same internal rhythm and leg turnover rate as an Olympic sprinter in the 100-meter final?
Fundamentally, yes. Your legs are swinging forward in the air at roughly the same speed as the fastest humans on Earth.
That is wild to think about. So if the fastest humans aren't moving their legs significantly faster through the air than the rest of us, what is the secret?
That's the big question.
Right. How are they reaching 27 miles per hour while the rest of us are barely cracking 10?
What's fascinating here is that the real difference is entirely about ground reaction force.
Ground reaction force?
Yes. The secret to human speed isn't moving your legs faster, it's maximizing how much force you can punch into the ground in a fraction of a blink.
It all comes down to the impact.
Exactly. It's about that tiny window of time when your foot actually makes contact with the track. Elite sprinters are driving a massive amount of force, specifically 4 to 5 times their own body weight into the ground.
4 to 5 times their body weight. That's huge.
And they are doing it in a window of just 90 to 130 milliseconds.
Just to give you an idea of how incredibly fast that is, if you pull out your phone's stopwatch and try to hit start and stop as fast as humanly possible, you will probably clock in around 120 to 150 milliseconds.
That really puts it into perspective.
Right. In less time than it takes you to double tap a photo on your screen, an elite sprinter is turning their leg into a piston, absorbing the impact and driving roughly 800 to 1,000 pounds of force back into the earth.
To visualize how the body actually handles that, Velocity Sports Performance uses a really helpful bouncing ball analogy.
Oh, I love this analogy.
It worked so well. Think of throwing a stiff rubber super ball at the ground versus throwing a soft, slightly deflated beach ball.
The super ball bounces incredibly high.
Exactly. Fast runners are essentially acting like that stiff rubber super ball. Their muscles and tendons don't just absorb the heavy impact, they store it as elastic energy.
Which gives them that explosive rebound.
Yes, in fact, that tendon elasticity provides 30 to 50% of the total energy required to run.
And the slower runners.
They are like the beach ball. Their limbs are too compliant, meaning they just absorb the impact without rebounding efficiently.
So the stiffer the leg, the bigger the bounce, and the faster you go.
Exactly. And that mechanical stiffness allowed Dr. Wayne's team to calculate a theoretical maximum speed for humans.
This is where the math gets crazy.
They ran an experiment where subjects hopped on a treadmill on one foot. Hopping allows for a longer aerial time and lets the leg generate maximum biological force.
So they isolated the absolute peak force the human leg can handle.
Right. They took that absolute maximum hopping force and calculated what would happen if a human could apply that exact amount of force with every single running stride while maintaining sprinting mechanics.
And the math on that is staggering. If a human could perfectly apply their maximum hopping force on every single stride, they could theoretically hit a top speed of 19.3 meters per second.
Which is insanely fast.
Translating that into track terms, that is a 5.18-second 100-meter dash.
Which borders on science fiction. But obviously there is a catch.
There's always a catch.
Actually applying that perfect maximum force while maintaining your balance and moving forward is the tricky part. It is not just about stomping the ground vertically as hard as you can. Direction matters immensely.
Right, because if you just bounce straight up, you aren't getting down the track. You have to translate that Super Bowl bounce into forward momentum.
Dr. Jean-Benoit Marin actually conducted a study looking at this exact problem.
The one with the French sprinter.
Yes, Christophe Lemaitre. He ran a 10.35-second 100-meter dash during their treadmill testing. The study found that Lemaitre didn't just produce more overall force than average athletes.
He was highly efficient with it.
Extremely. He produced 8% more mechanical power than his national level peers and a staggering 36% more power than non-specialist athletes.
But the real insight was how he applied it, right?
Exactly. He was exceptionally good at generating highly effective horizontal force. He perfectly oriented the force of his foot strike backward to propel his body horizontally forward rather than wasting energy bouncing vertically.
Here's where it gets really interesting, because when we talk about perfect mechanics, perfect symmetry, and optimal force application, we have to talk about the man who completely broke all the rules.
Usain Bolt.
Yes. The Locomotor Lab did a massive deep dive into Bolt's mechanics, and their findings essentially threw decades of coaching wisdom out the window.
It really caused a stir in the sports science community.
For a century, track coaches have preached perfect symmetry. Your left side should perfectly mirror your right side to maximize efficiency and prevent injury. But Bolt's running gait is entirely asymmetrical.
When researchers analyzed his world record sprints, the data showed his right leg hits the ground with 13% more peak force than his left leg.
13% is a massive difference at that level.
It is. Meanwhile, his left leg stays in contact with the ground 14% longer than his right leg.
Yeah.
He effectively has an uneven, galloping stride.
Wait, hold on. Are you telling me the fastest man in recorded human history essentially ran with a mechanical limp?
That's certainly one way to look at it.
How does that even work at that level of competition?
This is exactly what sparked a massive debate in the biomechanics community. On one hand, you have experts wondering if this was a mechanical flaw.
Meaning, if someone had corrected Bolt's stride early in his career to make it perfectly symmetrical, could he have been even faster?
Precisely. But on the other hand, many believe he intuitively optimized a natural physical asymmetry to become the fastest human in history.
So he figured out how to make an imperfection his biggest advantage.
That seems to be the consensus among many biomechanists today.
And what blows my mind is that his world record of 9.58 seconds might not have even been his ultimate biological limit. The environment held him back.
Yes, we have a mathematical model developed by Hans van Dyck that proves exactly that.
Van Dyck's model is fascinating.
It factors in the physics of air resistance alongside our physiological power limits. The human biological limit for sustained power output in these explosive events tops out around 6.35 watts per kilogram.
Okay, so 6.35 watts per kilogram is the ceiling.
Right. Van Dyke calculated that if Bolt had run his world record race with that exact same power output, but simply did it in the high altitude of Mexico City.
Where the air pressure is much lower.
Exactly, meaning air resistance is significantly reduced. He could have run a 9.36.
A 9.36, just from thinner air.
And if you add perfectly ideal tailwinds and ideal temperature conditions to that high altitude,
What does the math say?
the math says Bolt could have hit 9.18 seconds.
A 9.18 is almost unimaginable. But transitioning from the environment back to the human machine itself, let's look at how our bodies are physically built.
Body type plays a huge role.
We actually saw a perfect, real-world example of contrasting body types clashing on the track at the 2025 Tokyo World Athletics Championships in the 100-meter final.
That was an incredible race.
You had Oblique Seville, who was on the much shorter side at 1.70 meters tall. He was about 5'7", and he won the gold medal with a blazing 9.77 seconds.
Edging out the taller competition.
Exactly. He beat out Shane Thompson, who was significantly taller at 1.85 meters, and who ran a 9.82.
That race is essentially a masterclass in the science of stride mechanics.
Break that down for us.
If we strip running down to its most basic formula, speed simply equals stride length multiplied by stride frequency.
The times frequency.
Right. Taller runners like Thompson or Usain Bolt naturally rely on a massive stride length to cover ground.
Which gives them an advantage once they hit top speed.
It does, but because their limbs are longer and heavier, they have to constantly fight against sluggishness to maintain a fast turnover rate.
And the shorter runners.
Shorter runners, like Seville, naturally rely on explosive stride frequency. They can turn their legs over incredibly fast.
But they have shorter legs.
Yes, so to keep up with the taller guys, they have to punch massive amounts of force into the ground to artificially extend their stride length while they are floating in the air.
So if you are listening to this and wondering which of those two factors, stride length or stride frequency, you should actually focus on in your own training, science finally has a definitive answer.
The data on this is really clear.
A fascinating study by Sobarna and colleagues took two groups of runners and put them through a 6-week training program.
And they split the focus entirely.
Exactly. One group focused purely on training for stride frequency, doing rapid footwork drills and quick-step exercises.
The quick turnover group.
Right. The other group focused entirely on training for stride length, using explosive strength training and plyometrics to increase the amount of force they could push into the ground.
The results of that study were completely definitive.
Yeah.
Training specifically for stride length yielded incredibly higher speed gains.
It wasn't even close, was it?
Not at all. The stride length group improved nearly twice as much as the frequency group. They saw a 1.439 average gain compared to just 0.889 for the frequency group.
Which perfectly aligns with Wayan's research from earlier. Putting more horizontal force into the ground to maximize the distance you cover in the air is the single most effective way to get faster.
It really is the ultimate key to speed.
But because stride length is the ultimate key, it has also sparked one of the most intense controversies in modern athletics.
The prosthetic debate.
Yes, I am talking about the debate surrounding bilateral amputee sprinters, like Blake Leeper, competing in able-bodied events using carbon fiber prostheses.
It's a highly complex issue.
Because if speed is just an equation of length times frequency, altering your limb length artificially changes the entire math of the race.
Looking at this purely from the biomechanical data presented in the sources, it is a fascinating geometry problem.
What's the core issue biomechanically?
The core issue is that bilateral amputees can potentially use prostheses that are artificially longer than their natural biological proportions would dictate.
Which artificially inflates the stride length side of the equation.
Exactly. In Leeper's case, researchers found his running blades made him 15 centimeters taller than his estimated biological height.
So to clarify the math here, it's not about the carbon fiber being super bouncy or lightweight. It's strictly about the length of the lever.
Precisely. Because speed is stride length times frequency, having limbs that are artificially 15 centimeters longer grants an unnatural stride length advantage.
It completely changes the required mechanics.
It does. It artificially enhances their sprint times by allowing them to cover significantly more ground per step without having to generate the corresponding biological ground force that an able-bodied runner would need to achieve that same stride length.
It highlights just how incredibly sensitive the speed equation is to the physical length of the limb.
It really does.
But whether your limbs are natural or prosthetic, long or short, there is an invisible factor driving all of this from the inside.
The genetic code.
Yes, and that is your DNA. This brings up the classic debate. Is elite speed something you can build in the gym with plyometrics, or is it something you just have to be born with?
If we connect this to the bigger picture, it is undeniably a mix of both training and genetics, but you absolutely cannot ignore the genetic baseline.
The baseline sets the ceiling.
Exactly. Scientists have actually isolated what they refer to as the speed gene. Its scientific name is the ACTN3 gene, specifically a variant called the RS1815739 polymorphism.
It's a mouthful.
It is. But you can just think of it as the fast twitch builder. This gene codes for a specific protein, alpha-actinin 3, that is found exclusively in your fast twitch muscle fibers.
Which are the fibers responsible for explosive, powerful, high-force movements.
Exactly.
And the real-world data on this gene is incredible. A recent study by Mesita looked at professional elite football players.
A great demographic for testing explosive speed.
Right. They tested the players' DNA to see who had the speed gene, and then they tracked their actual maximum running speeds during official matches using high-frequency GPS trackers.
The results were stark.
The players who had the CC genotype, which is the optimal variant of this speed gene, reached a maximal running speed of 33.1 kilometers per hour.
Very fast.
But the players with the TT genotype, who lacked that specific protein expression, topped out at 31.5 kilometers per hour.
And at the elite level, a difference of 1.6 kilometers per hour is monumental.
It is the difference between breaking away from the defense for a goal or getting tackled from behind.
Absolutely. But having that CC genotype doesn't just make you faster, it provides massive protective benefits as well.
Protective benefits.
Yes. The study noted that players with the CC genotype experience a significantly reduced frequency and severity of eccentric muscle damage.
Eccentric muscle damage being what, exactly?
Eccentric damage is the wear and tear that happens when a muscle lengthens under tension.
Oh, like when you're trying to stop suddenly?
Think of the intense burning sensation in your thighs when you are running fast downhill. Your muscles are acting as brakes, absorbing massive force while stretching.
And the CC genotype helps with that.
It essentially acts like premium internal shock absorbers against that damage. Their muscles are literally built at a cellular level to withstand the violent, high-force impacts of sprinting without tearing or breaking down as easily.
That is a massive evolutionary advantage on the field.
It really is.
But obviously our biology encompasses more than just a single gene. Sex and age play a massive role in the biomechanics of speed as well.
They do, and the data paints a very clear picture of how performance gaps shift.
How so?
When we look at the performance gaps between elite male and female athletes, the biological gap actually increases as the sprint distance gets longer.
That's interesting. It's closer in the short sprints.
Yes. At the short 60-meter dash, the performance gap between elite men and women is about 8.6%. But stretch that race out to the 400-meter sprint, and the gap widens to 11.7%.
Why does distance change the gap?
As the distance increases, the physiological demands shift from pure, explosive force generation to a complex mix of power and anaerobic endurance, where biological differences in muscle mass and oxygen delivery systems become much more pronounced.
That makes perfect sense. But speaking of biology and age, we absolutely have to talk about the legend from the sources who proves that getting older doesn't mean your muscles forget how to fire.
Oh, this is one of the most inspiring pieces of data in the entire deep dive.
I love this story.
In May 2024, a 91-year-old Italian woman completely shattered the world record for the 90-plus age category in the 200-meter sprint.
91 years old.
Yes, and she ran it in 51.47 seconds. She didn't just edge out the previous record, she crushed it by 1.5 seconds.
To put that in perspective, running 200 meters in 51 seconds at 91 years old requires a level of biological efficiency that most people assume is impossible at that age.
It defies conventional expectations.
How is she doing that if muscle mass naturally declines as we get older?
That is exactly what researchers, including Dr. Simone Porcelli and Dr. Christopher Sundberg, wanted to know. They actually took muscle biopsies to study her cellular makeup.
And what did they find?
What they're finding is that while we do undeniably lose raw muscle mass as we age, high-level neuromuscular adaptations can be preserved.
Neuromuscular meaning the connection between the brain and the muscle.
Exactly. This means the brain's wiring to the muscles, its ability to efficiently recruit those fast-twitch muscle fibers and coordinate that stiff, bouncing, elastic stride we talked about earlier, can be maintained through an entire lifespan if you keep actively using those pathways.
Her brain still knows exactly how to tell her legs to act like a Super Bowl.
She kept the pathways active so the body remembered how to bounce.
So what does this all mean? Let's bring this all together for you. If you are lacing up your shoes today, whether you are training for a local marathon, trying to dominate your weekend sports league, or you just want to understand the miracle of the human machine.
Your speed is dictated by a few incredibly specific things.
Exactly. It is about the stiffness of your tendons acting like a rubber ball. It is about the sheer, massive, horizontal force you can punch into the ground in 1/10 of a second.
And it is heavily influenced by your genetic baseline and your stride geometry.
Right. And if you are hitting the gym, the science definitively says you should be training to increase your stride length through explosive power, rather than just trying to cycle your legs faster in the air.
This raises an important question, though.
Let's hear it.
We have spent this deep dive looking at the absolute limits of human biology. We now have a mathematical model of perfect running physics. We know that Usain Bolt, the fastest man ever, achieved his records by utilizing a mechanical asymmetry that defied traditional logic.
Right.
And perhaps most importantly, we have isolated the exact ACTN3 gene that grants top-tier speed and protects against muscle damage. As gene editing technologies like CRISPR continue to advance at a rapid pace, what happens to the future of the 100-meter dash?
Oh, wow.
Decades from now, will the first human to finally break the 9-second barrier be a natural-born athlete who simply won the genetic lottery? Or will they be engineered in a laboratory specifically designed to apply 5 times their body weight into the track?
That is a wild thought to leave on. Are we currently watching the last generation of purely biological sprinters?
It's certainly possible.
We will leave that for you to ponder.
Thank you so much for joining us on this deep dive. Keep questioning the world around you and keep exploring the incredible limits of human potential. We will catch you next time.